Dear students, in this video let us learn about the physiology of hearing. Actually, in the entire ENT subject, there are very few topics that are conceptual. Most of them are theoretical, very simple to understand, and if you just go through them once, you're done. And certain topics are slightly memory based, but very few are conceptual. And physiology of hearing is one such conceptual topic. It requires an understanding about how things are happening, okay? So, and it's also one of the often avoided topic by medical students. It's just ignored and scrolled through. Probably because of two reasons. One is it's not very important from direct questions per se from the exam. I mean, nobody will ask you to explain about the physiology of hearing, but it has lot of clinical implications. If we understand the physiology of hearing properly, we would be able to understand better about types of hearing loss. We would be able to understand better about the assessment of hearing and so many other diseases. So that way physiology of hearing is important. And another reason why people avoid it is probably because it's complex to understand, okay? So once and for all, let us properly understand this topic. So for the next few minutes, drop your pens down, gently close that book, and with rapt attention, just listen to me. When you have to write down, I will let you know, okay? So let us begin from the very basics. What is sound? Any vibrating object will cause waves of compression and waves of rarefaction, and it is capable of producing sound. Now my vocal cords are vibrating, and that is why sound is coming out. Any object, any sound comes from the same mechanism. Vibration will produce sound, okay? So that is fact number 1 that you have to understand. In physiology of hearing, fact number 1 that we have understood is that any vibrating object is capable of producing sound. How does it produce sound? By causing waves of compression and rarefaction. Okay. Now, second fact that we have to understand is sound, we all know, travels in air, travels in the medium of air. But it also travels in liquids and solids. In fact, it travels faster in liquids and even faster in solids than in air. Okay. So, this is fact number 2, that sound travels in air, liquids and solids. Okay. Then there is fact number 3 that we need to understand. That is, when sound travels from one medium to another medium, say from air to liquid or liquid to solid, some amount of sound energy is lost when it is traveling from a thinner medium to a denser medium. When it is traveling from air to liquid, let us say, air is a thinner medium and fluid is a denser medium. So when it is traveling from air to fluid, some amount of sound is reflected and some amount is transmitted. Large amount is reflected, a small amount only is transmitted. So all in all, there is a loss of sound energy. Some amount of sound energy is lost at that interface when it is traveling from air to liquid. Yes, this part is clear? This is our fact number 3. When sound travels from one medium to another medium, such as from a thinner medium to a denser medium. Now thinner medium here for us is air and denser medium is liquid. Air to fluid or liquid. Some amount of sound energy is lost. Okay. No confusion so far? Why some amount of sound energy is lost? Because the fluid medium offers resistance to this sound. And that resistance is called as the resistance offered by the fluid medium, offered by the denser medium to sound is called as impedance. Clear? What is impedance? It is the resistance offered by the fluid medium when sound is traveling into it from a thinner medium such as air. That resistance is called as impedance. Okay. Now why are we learning about sound and physics in ENT? I'll make you understand. Because sound is traveling in the air. That is collected by our external ear and middle ear. Until then, so far so good, because that is all air. But once it goes into the inner ear, what is the inner ear filled with? Fluid, perilymph, endolymph. So it has to change the medium. From air medium, it is going into fluid medium. And that change doesn't happen easily. All the sound energy is getting lost there at that interface. Impedance is being offered by the inner ear fluids to middle ear sounds. Okay, that is why we are learning these facts. Clear? Okay. So, now let us look into mechanism of hearing. Mechanism of hearing. Now the mechanism of all the 5 special senses are special. You know, the way we perceive sight, the way we perceive smell and taste, and how we hear, they're all very fascinating to understand. And vision and sight are, and vision and hearing are particularly fascinating. And I would say mechanism of hearing is slightly more complex to understand than the mechanism of vision also. So let us look into it. It can be studied under 3 headings. You might write this down if needed. Otherwise, you can write everything at the end of the video. But attention is most important. So the first step that occurs in the mechanism of hearing is mechanical conduction of sound. Mechanical conduction of sound. The sound waves from the external environment are being mechanically transferred to that final sense organ inside the inner ear. So, this process is done by the conductive apparatus. Okay? This is by the conductive apparatus. Now, next step is, these sound waves that have been conducted, they have to be converted. That is, transduction of mechanical energy into electrical impulses. What is mechanical energy? Sound waves. It has to be converted into electrical impulses because our brain, our nerve cells can only read electrical impulses. It is converted to electrical impulses. And how is this done? By what is this done? It is done by the sensory system of cochlea. Cochlea is the actual part that hears the sound, right? So the sensory system of cochlea converts this mechanical energy into electrical impulses. And the final step is the converted electrical impulses have to be transferred to the brain, to the auditory cortex present in the brain that finally reads the information. So the last step is conduction of electrical impulses to the brain. And by what is this done? It is by the auditory pathway. We can learn this by studying about the auditory pathway. So these are the three steps. First, the sound has to be captured from the external environment and it has to be converted till the organ of Corti, the final sense organ. And that organ of Corti, the sensory system of Cochlea, will convert this mechanical energy into electrical impulses. And then the electrical impulses via nerve cells are transmitted to the brain, to the auditory cortex of the brain, which finally reads the information. So let us study about all of them one by one. First part, mechanical conduction of sound. This is done by the conductive apparatus. Mechanical conduction of sound. The sound from the external environment is collected by the pinna, which is also called as auricle. That is the first step in our pathway. The auricle or pinna collects the sound from external environment. Next, after the auricle, we have the external auditory canal. The sound waves travel via the external auditory canal and then they go and hit the tympanic membrane, the ear drum. And what this drum does? It vibrates. And embedded in the tympanic membrane is the handle of malleus. The manubrium of malleus is embedded in the tympanic membrane. So when the tympanic membrane vibrates, these vibrations are automatically transferred to the malleus. And articulating with the malleus is the incus. And articulating with the incus is the stapes. So automatically, once the malleus receives those vibrations, they travel all through the ossicular chain until they reach the foot plate of stapes. Final part is the foot plate of stapes. Foot plate of stapes is in communication with oval window. Okay. And after the oval window, the next part is the inner ear. So far so good. And now the inner ear is filled with fluids, perilymph, endolymph, all these fluids are there. What happens in the inner ear is part 2 of the story. Before we move on to part 2 of the story, we need to understand one very important fact here, that until now it was in air medium and in the inner ear it is going into fluid medium. And when it is going from air to fluid, what happens? The sound energy is greatly reduced. The sound becomes dampened. So, we have to overcome this. We can't let all the sound that we have collected be lost at the interface and only very small amount to reach inside. We cannot hear such small vibrations. So what we do is, the middle ear does something here. The main objective of the middle ear is to convert high amplitude, low force vibrations. High amplitude, low force vibrations to low amplitude, high force vibrations. This is the basic function of middle ear. Low amplitude, high force, greater force vibrations are created. And why is the middle ear doing this? To overcome the resistance offered by the fluid medium in inner ear. Can I say to overcome the impedance? Yes. So this function of middle ear is called as Impedance matching. Impedance matching. Impedance matching mechanism, or it is also called transformer action. Transformer action. What the transformer does? It is present in the middle of the pathway and it converts A to B. Here it is converting high amplitude low force vibrations into low amplitude high force vibrations. This is the function of middle ear, and the same thing is called as impedance matching mechanism. So when there is a question about what is impedance matching, we no longer need to get bogged down. This is the basic function of impedance matching. It is converting high amplitude low force vibrations to low amplitude high force vibrations. Why? To overcome the resistance offered by the fluid medium of inner ear, to overcome impedance. That is impedance matching. But an even more important question is, how is it performing this function? How is the middle ear overcoming this impedance? By three mechanisms. Let us see what they are. The first mechanism is called as lever action. It is called lever action. What is lever action? You have observed the pictures of malleus, incus and stapes. Malleus is the largest of all three of them. It is very long. Incus is relatively short and stout, isn't it? And stapes is a small bone. It has a completely different shape. So when sound is moving from malleus to incus, what happens is the long process of incus I'm talking about. The long process of incus is shorter than the handle of malleus. This fact must be remembered. The long process of incus is shorter than the handle of malleus. Okay? The handle of malleus is 1.3 times longer than the incus, than the long process of incus. So for you to easily understand, if I say the handle of malleus is 1.3 centimeters, long process of incus is only 1 centimeter. So 1.3 times it is longer, and this gives a mechanical advantage. Now if you are still not able to understand the ramifications of this fact, if a bigger object hits a smaller object, now this smaller object can only vibrate in its amplitude. But the force, where will all the force go? The bigger object obviously has larger force, and when it hits a smaller object, the smaller object will vibrate with its maximum amplitude, but its amplitude is small, its range of motion is small. What is amplitude? Maximum displacement. Say the amplitude of this pen is this much. It can move maximum up to this point. It cannot go beyond this. This is the amplitude of this pen. Maximum displacement is called as amplitude. So maximum displacement of that small incus bone is less than the maximum displacement of malleus. So when malleus is hitting incus with all that force and incus cannot displace beyond, what happens? The force automatically increases. Yes? When this force increases, our purpose is achieved. And by how much? 1.3 times. So their difference in size offers a mechanical advantage of 1.3. Okay, this is one mechanism. The next mechanism is called as hydraulic action. Of tympanic membrane. What is hydraulic action? Those of us who thought we are done with physics at 12th class, I'm sorry to say we are going back there. So let us see what it is. It's pretty simple. There is an area difference between the tympanic membrane and the stapes footplate. Now from where to where is the sound going? It is beginning at the tympanic membrane. Via the 3 ossicles, it is going into the oval window. Yes. So the area of tympanic membrane is much bigger than the oval window. You can see that in any picture that you observe. Yes. So if I compare the area of tympanic membrane to the area of stapes footplate or the oval window, they are in the ratio of 21:1. Okay. 21:1 is the ratio. There is so much of discrepancy in the size between the small oval window and the big tympanic membrane. But the entire tympanic membrane does not vibrate. The effective area of vibration of tympanic membrane is only the middle part of it. And those two, if we compare, the ratio is 14:1. What is this 14:1? Effective area of vibration if we compare. Okay. According to some authors, the ratio is 55 millimeter square is to 3.2 millimeter square. How much is that? 3.2 into approximately, I can say 17 times is the ratio. So 55:3.2 is 17:1. This is the effective area. Of vibration. So the difference is 17:1. Please do not get confused by all these numbers. 21:1 is the actual area ratio. But the entire tympanic membrane does not vibrate. Okay. Only some part of it vibrates, and according to some schools of thought, it is 14:1. And some people say the effective area of vibration of the drum is actually 55 millimeter square. And so the ratio becomes 17:1. Okay. They are just two discrepancies that exist worldwide. Okay. So what we have to understand here is, by the lever action we have got an advantage of 1.3, and here by the hydraulic action we have got an advantage of 17. So if we multiply both of them, what is the final advantage? 17 into 1.3, and that is 22.1. This is the final mechanical advantage that we have gained. Now what does this translate to? 22:22.1. The sound that we are hearing is being amplified 22.1 times because of the mechanical action of middle ear. Because of these two features of middle ear, the sound is being amplified 22.1 times. And the middle ear doesn't stop there. There is another mechanism, that is the curved membrane effect. What is the curved membrane effect? Now, while learning about the anatomy of tympanic membrane, I have told you that the tympanic membrane is not just a circle sitting there in the annulus tympanicus. Because of the attachment of the lowermost point of handle of malleus at the point of umbo, it is drawn inside. So the tympanic membrane is actually curved inside. It is not a plane. It is not a plane circle. The central part is pulled inside. So there is a curved membrane effect. What happens because of this? The movements of the tympanic membrane are more at the periphery than at the center. Because of this curved membrane, the movements of tympanic membrane are more at the periphery than at the center. And this also gives us some advantage. It cannot exactly be measured, but this curved membrane also increases the force and decreases the velocity. This is what we want. We want the force to increase so that at the interface, even if some amount is lost, the final vibrations that reach the inner ear will be adequate for us to hear the sound. So this is about the curved membrane effect. Finally, we have three mechanisms, and they are the lever action, because the long process of incus is shorter than the handle of malleus, that is the lever action. And second is hydraulic action of tympanic membrane, because the effective area of vibration of tympanic membrane is more than the footplate of stapes by a ratio of 17:1. That also provides a mechanical advantage, and if we multiply 17 with 1.3, we finally get an advantage of 22.1. So the sound is amplified 22.1 times, and also the tympanic membrane being curved adds to this. And finally, the sound is greatly amplified because we are losing some sound at the air fluid interface. The middle ear is doing something to prevent that loss. It is amplifying sound, which is called as impedance matching action of middle ear, transformer action of middle ear. And how is it doing it? By these three mechanisms. Apart from that, we need to understand a few more things. There is a concept known as phase difference between the two windows. What are the two windows? Round window and oval window. Or the same concept is also known as acoustic separation. Acoustic separation between the two windows. What is this acoustic separation? So the sound waves which are striking the tympanic membrane will travel via the middle ear, and they do not reach the oval window and round window simultaneously. There is a preferential pathway to the oval window via the ossicular chain. The sound waves striking the tympanic membrane do not reach oval window and round window simultaneously. There is a preferential pathway to oval window. So, when the oval window receives a wave of compression, the round window receives a wave of rarefaction. So, when the oval window receives a wave of compression, the round window receives a wave of rarefaction. If at all both the windows receive simultaneous waves, then these two waves cancel each other and no sound will be heard. So, it's important that the oval window and round window receive waves at different times, and that is called as phase difference, or it is called as acoustic separation. If at all they reach simultaneously, if waves reach simultaneously, they cancel each other and no sound is heard. This acoustic separation is possible only when the tympanic membrane is intact along with the three ossicles and the middle ear is functioning properly with air. That is, the eustachian tube is sufficiently aerating the middle ear. Because via the ossicles, the sound travels faster and reaches the oval window, whereas the air in the middle ear causes some lag and the round window is stimulated later. Okay, and this acoustic separation gives an amplification of 4 decibels. 4 decibels. When the tympanic membrane is intact and when there is air in the middle ear. These two factors are very important. Now, while studying certain diseases, when one of the windows is not functional or something has happened to this pathway, you will understand how it affects hearing. Then there's another concept that we need to learn that is called as natural resonance. What is natural resonance? Every object has its own resonance, its matching frequency. Similarly, the external ear and the middle ear also have their own natural resonances. Let us see what they are. As you can see in this table, the external auditory canal has a natural resonance of 3000 Hz. Tympanic membrane has a natural resonance of 800 to 1600 Hz. And the ossicular chain has 500 to 2000 and the middle ear has 800 Hz. These are their natural resonances. Now, why is this natural resonance important? Now, these structures allow certain frequencies to pass more easily than certain other frequencies. Suppose the external auditory canal anywhere around 3000 Hz, it will allow them to pass easily because it is matching with its own natural resonance. Okay. Similarly, the tympanic membrane would be favorable towards any frequency between 800 to 1600. Now, why is this entire concept important to us is because if you observe the range, it is between 500 to 3000 Hz. And this is also our speech frequency, the frequency that we need to hear maximum, 500 to 3000 Hz, and that is matching with the natural resonances of the external and middle ear. So this also gives an advantage. So we have now understood about all the concepts in the first part, the conductive apparatus, how the sound has struck the tympanic membrane and has been transmitted all the way till the oval window, and in between what the middle ear is doing to overcome the impedance, and also some other added advantages because of phase difference and natural resonance. After the sound strikes the inner ear, strikes the oval window, then it is transmitted. What is in contact with the oval window? Scala vestibuli, perilymph. And from the scala vestibuli, now scala vestibuli on one side has bone and on the other side it has the Reissner's membrane which is separating scala vestibuli from scala media. And the Reissner's membrane is a thin membrane. These sound vibrations cannot cross the bone and go elsewhere. They affect the Reissner's membrane. And then they travel upwards all along till the apex. And then they come into the scala tympani also. And scala tympani and scala media are separated by basilar membrane. Now these vibrations are transmitted to the basilar membrane, and inside the basilar membrane is the organ of Corti, the main sensory organ for hearing. So let us study about how it travels in the inner ear and how those impulses are converted into electrical impulses by the organ of Corti, and how these impulses are transmitted to the brain via the auditory pathway in the next video. So for now, it is important for us to understand about impedance matching and some basic concepts about sound. Okay, thank you very much. Catch up in the next video.